So today we're going to talk about continuous random variables. Such examples of continuous random variables in the world: speed of a car, concentration of a chemical in a water sample, heights of people in a population, lengths of areas of manufactured components, measurement errors, electricity consumption in kilowatt hours. So let X be a sample space of an experiment. A continuous random variable is a function when it's set up all possible outcomes of the experiment to the real numbers and associated to each continuous random variable is a probability function, or more precisely call it a probability density function, such that so uh, f of x is always going to equal 0. The area underneath the whole curve is always equal to 1. So don't worry too much about the inverse sign. The inverse sign just means the area under the curve. Okay, so this just means the area under the curve. Under curve from minus infinity to infinity. And the probability that x is in between a and b is given by the area under the curve from of y to fx from x to a to x to b. So you can see that here in the probability that so this is the represents the probability that x lies in between a and b. The probability that x lies in between a and b is written like this. Note that the probability that a certain continuous random variable equals to a certain number is in fact equal to 0, since the area under the curve from a to a is equal to 0. And finally, the probability that x is less than a is just the area under the curve from minus infinity to a. So, for example, let's take the following example of lead concentration in Hong Kong gasoline. Suppose it ranges from 0.1 to 0.5 liters. And suppose X represents the concentration of lead in Hong Kong gas. And it has the following probability density function. So suppose f x to 12.5x minus 1.2 for x in between 0.5, 0.1 and 0.5 and 0 elsewhere. Find the probability that the lead concentration in randomly selected liter of gasoline will lie in between 0.2 and 0.3. Well, first, let's just draw the probability density function. So then we have that. And so kind of look like this. It starts in 0.1 to 0.5. And it goes with a slope of 12.5, so it's kind of like this. And we want to find basically the area under the curve, right? From 0.1, from 0.2 to 0.3. So we kind of want to find this area. Okay. So this is your y x. So the probability that x lies in between 0.2 and 0.3 is area of the yellow region. So we can just use the triangle formula. There's a we can figure out the triangles here. There's a big triangle here, and then a big right angle triangle here. There's a big right angle triangle here, minus the area of the smaller right angle 0.1, 0.3, and this is height f of 0.3. So this is height. This has height f of 0.3. This is height f of 0.2. This is 0.1 and 0.2. So in fact, so this is just is equal to half base times height. So 0.3 to 0.3 minus 0.1 times height of the bigger triangle, which is f of 0.3 minus half base times height 0.2 minus 0.1 times height, which is f of 0.2. So in fact, this is 0.1 times 12.05, oops, 12.5 times 0.3. We plug it into the f formula, minus 0.05 times 12.5 times 0.2 minus 1.25. We plug that into a calculator, 0.1875. That's probability that the lead in Hong Kong gas is in between 0.2 and 0.3 grams per liter. So with every random variable, we can associate a mean or expected value and a variance, just like in the discrete random variable case. So when we go from discrete to continuous, the sum turns into an integral sign. So this is so that's why we have this infinite or infinite integral. But you don't need to worry about the integral. This we're not going to compute any integrals in this course. But basically, it's the same thing. It's the sum of x times f of x, okay? And same thing with the variance formula. It's the sum, if you want, of x minus mean square times f of x, and then you sum over all the possible values of the continuous random variable. And we have this alternate formula too, which we have for the discrete random variable case, which is the variance is the expectation of x squared minus the mean square. In fact, in general, the expectation of any function of a random variable, h of x, is the sum if h of x times the probability density function f of x, and then you sum over all the possible values of the continuous random variable. Now let's look at a common continuous random variable distribution called the uniform probability distribution. Such examples are the simple time it takes for you to board an MTR train. So the probability density function here is a simple rectangular shape. So in fact, f of x equal to suppose the continuous random variable has a uniform probability distribution on the interval AB if its probability density function is the following piecewise defined function form, is equal to 1 over b minus a, okay, or x in between a and b, and 0 otherwise. So in fact, it just looks like this. Just looks like a rectangle. Okay? So it's 0 elsewhere. So note that the probability, the area underneath the probability density function is equal to 1. Area under f of x from minus infinity to infinity is equal to 1. So In fact, the mean of a uniform probability distribution is just you can calculate to be a plus b divided by 2. And the variance would be, in fact, just b minus a squared divided by 12. You can do this pretty simply. So you can show that for the probability that x lies between c and d for a uniform probability distribution is just d minus c times 1 over b minus a. So base times height, basically. So this is the area of this region. And similarly, probably that x is greater than c is 1 of the base, which is b minus c times height, 1 over b minus c. Same thing, probably that x is less than c is, this is the height of the rectangle, this is the base of the rectangle. For example, suppose x is uniformly distributed between 0 and 10. Calculate the probability that x is less than 3, x is greater than 6, and x is in between 3 and 8. Well, we see that by definition, the probability density function has to have the following form. Fx equal to, so we can actually draw it out. Is 0 to 10. So by definition, the height of this uniform probability distribution has to be 1 over 10. Right? 1 over 10. So it looks like this. That's just the f of x here. So let's calculate the probability that x is less than 3. Well, this is just this area here. Right? This is 1 over 10. This is 3, so you're looking for this area. So clearly that's going to be this base times height. Right? 3 minus 0, which is 3 over 10. Same thing, was probably the x is greater than 6. Well, we're looking for this area. So this is 10, this is 1 over 10. So from 6 to 10, you're looking for this area. Height times base, which is 10 minus 6. Is 4 over 10, which is 2 over 5. And finally, what's probably that x is in between 3 and 8? Again, you're looking for this area. This is 1 over 10. This is 10, so it's 3. This is 8. You're looking for this area. So again, height times base is 3, which is 5, 10, which is a half. So let's do an application of the uniform probability distribution and ask the following question. Suppose buses arrive at a Hongham bus station at 15-minute intervals, starting at 7 a.m., 7:15, 7:30, 7:45, etc. Okay. Now, if a passenger arrives at the bus stop at a uniform distributed between 7 and 7:30, okay, find the probability that he waits less than 5 minutes, okay, less than 5 minutes for the bus, or more than 10 minutes for the bus. So you think, that the probability is, you think the probability that he waits less than 5 minutes is less than the probability he waits for more than 10 minutes? you think the two probabilities are the same, or you think that the probability he waits less than 5 minutes is greater than the probability that he waits more than 10 minutes, or none of them. In fact, the answer is so something that might not be too obvious, but in fact, the probability is equal. So how do we show that? Okay, so so y is the probability equal waiting less than 5 minutes is equal to probability of waiting greater than 10 minutes. I'll show you why. So in this case, we have a uniformly distributed random variable. Okay. So let x, for example, let x be your or let z, sorry. Let z be your time we arrive at the bus stop after 7 a.m. Then probability that you wait less than 5 minutes is equal to probability that you come at 7:10 and 7:15, because if you come during this time 7:10 and 7:15, you just wait less than 5 minutes for the 7:15 bus to come in. And also you have to add the probability that you come in between 7:25 and 7:30, because again, if you come in between 7:25 and 7:30, the next bus comes, or MTR comes at 7:30. But we know that the probability density function in this case, f of x is at the form 1 over 30 minus 0 for z in between 7 o'clock and 7:30, and 0 otherwise. Right? So therefore, this is just equal to base times height, which is 1 over 30. Same thing here. This is base times height. So this is just 10 over 30, which is 1/3. So you have 1/3 probability of waiting less than 5 minutes for the bus. Similarly, probably that you wait for greater than 10 minutes for the bus to come is same as the probability that you come in between 7 o'clock and 7:05, because 7:15 comes the next bus, right? So you come in between these times, then of course you wait for greater than 10 minutes. Plus probably that you come in between 7:15 and 7:20, because the 7:30 bus comes next if you come 7:15 to 7:20. And this is just base times height. That's base times height. Okay. So again, this is also 10 over 30. So in fact, remember, this is just your x, probably that you wait less than 5 minutes. This is your y, and this applies. The probabilities are the same.